Hello, everyone. Welcome to Teens to Moscilloscope 4.1. It's a Teensy 4.1 microcontroller-based oscilloscope. In this project, we had 5 engineering requirements that all other groups had. Our 2 extra that we added was that the system would display the peak-to-peak voltage and period of the waveform. The system will weigh less than 7 pounds. Our challenges was that using a single PCB required a lot more work to fit everything on one board, and our bandwidth ended up not matching our simulation, as well as the trigger and signal processing conflicted with each other. Future considerations was to make a multi-layer PCB board so that there's less noise and better front end, as well as using an external ADC so that there's a higher sampling speed. Here's a diagram of our top level architecture. As you can see, 2 blocks per person. Our goal of the front end was to take analog signal and user inputs and then convert them to the microcontroller. There's 3 different power inputs, 2 channels for analog, 4 buttons, and 2 rotary encoders. Users would physically manipulate the buttons and encoders. The 2 rotary encoders each had a switch, and the rotary encoders had 2-bit quadrature to communicate with the microcontroller. Everything here was active high for the buttons and the encoders. Here's the section for the front end outlined in blue. For the front end signal processing, the goal was to buffer and attenuate with the voltage shift up. We simulated a bandwidth past 300 kilohertz, but it turned out to be 30 kilohertz in reality. Here's a diagram in the top showing our output to be 0 to 3.3 within that range. And in the bottom, our frequency response, negative 3 dB, went past 300 kilohertz. For the microcontroller, the goal was to sample and input analog signal from the front end and digital signals. We used Teensy 4.1, which had 2 10-bit ADCs and a high clock. And we used digital bullet pins for the front end and digital pins for communication with display. Here's the section on the PCB board with that.
For the code block, it's all about data in and data out, more specifically to process all the front-end data into usable data points, signal measurements, and display code for information. For the data in, it receives raw ADC data that we sample each ADC in parallel 4,000 times, and we use that 4,000 value array to reconstruct waveforms for the oscilloscope. In addition to the analog signal, we get digital signals from the front end, which represents our user input from the rotary encoders and push buttons. For outputs, it condenses down the 4,000 values that we sample into 320 plottable points. That's for the 320 pixel wide display that we use. In addition to that, user input instructions are stored in global variables, which shows up later in the display block as indicators to the user, as well as waveform measurements that we take from the 4,000 samples for the peak-to-peak voltage and the period. Some challenges that we ran into this block was measurement noise. So when we fully integrated this block with the rest of the electronics, we had issues where our peak-to-peak voltage and our period measurements required the wave to be consistent at all times, and we had issues adjusting our algorithms to make sure we were correctly measuring. In addition to that, implementation of several libraries across the ADC, software graphics, and front end was difficult. Looking at the display, the goal was to accept all the oscilloscope's information for display on an ILI 934 TFT display. So it takes in the 320 voltage points that the code block outputs, as well as measurement values for the peak-to-peak voltage and period. Then finally, with that, it takes the user input indicators, which are global variables, and to the user, that looks like their ability to navigate around a menu. For outputting, it takes all that requested information displays it on screen for the user to look like an industry standard oscilloscope. Some challenges we ran into was broken hardware. We had 2 displays that were problematic throughout the process. In addition to that, the scale of programming, specifically the graphics, took over 1,000 lines of code.
For power block, we have 2 goals. We have 3 main goals: providing 5 volt, 3.3 volt, and negative 5 volt for the whole system. We also wanted to be high efficiency because we wanted to be able to run on a 9-volt battery also. Some challenges we have is actually the inherent noise from the switching buck converter and also the noise from the voltage inverter for negative 5 volts. And to address the the noise from switching buck converter, we actually use like a second stage LDO. And for the noise from the voltage inverter, is actually using a second order pipe filter. And on the right block, you can see that's a buck converter, and on the right is actually the second stage LDO. And for the enclosure, we have 2 main points: is actually protect the system from the environment, and also most importantly, is actually protect the user from potential electric shocks. And the challenge is actually tight tolerance between the LCD and TNC, also with the user input. And the other thing is actually the alignment of the mounting points due to like thermal expansion and contraction due to like the 3D printing process. And on the left is actually our design, and on the right you can see like the clearance between the LCD and the TNC is only around 4 millimeters.
Then finally, reiterating some of our achievements, we achieved very nice low latency. So we were able, in addition to sampling those 4,000 samples in 5 milliseconds, we were able to take the user input also at a very fast rate. So to the user, it seems that the instant that they push that button, the oscilloscope responds. For sampling rate, we were able to achieve over 200 kilohertz, which both fulfills the engineering requirement that we were up against, but also makes us proud that we were able to hit that sampling speed with our ADC software and our hardware. In addition to that, we have a very friendly user interface that is easy to navigate. So it's meant to replicate an industry standard oscilloscope with a menu, scroll buttons, and push buttons that are intuitive to how the user might interact with a normal oscilloscope. And then finally, we kept the whole cost of the project low at about $180, which represents a high functioning project for not that expensive of a cost. That's all, folks.